from the University of Illinois, Chicago, who will be sharing her PhD work with us. And to introduce her, is a member of her group out in Dr. Thomas Searle's group at UIC, Dr. Sanjay Lohani, who's a postdoc in the group there. Okay, Sanjay?
Yes. Hi, everyone. So yeah, as I said, I'm Sanjay Lohani, and I'm introducing Ashley and we have Professor Searles today. So yeah, with the special excitement, I'm pleased to introduce Miss Ashley Blackwell to this featured talk. And Miss Blackwell obtained her bachelor's in physics at Dillard University, and she is now a PhD candidate in the electrical and computer engineering department at University of Illinois, Chicago, where she recently transferred from Harvard University in 2021. And while at Harvard, she completed 2 consecutive internships with the U.S. Naval Research Laboratory, where she was awarded the Quantum Information Science and Engineering Network Fellowship for 3 years. She also obtained the GM Fellowship in 2020 and interned at the Commonwealth Edison Company, which is COMED, where she worked on quantum algorithms for potential use in the power grid system. And most recently, she interned at IBM Quantum, where she worked on a client's API connection to use IBM's real quantum computers. And today, she is going to talk about her current dissertation at UIC and a collaborative project with IBM, which is entitled as Hardware-Aware Studies of Quantum Black Box Algorithm. So please join me in welcoming Miss Ashley Blackwell. So, thank you.
Thank you, Sanjay. That was wonderful. Hello, everyone. My name is Ashley Blackwell, as mentioned, and it's plastered all over the place. As you mentioned, I am a 5th-year PhD student in the EC department, where, I'm going to be doing some, my talk is going to be on these hardware-aware studies of quantum algorithms. But first, I do want to go a little bit into my background just to kind of, get everyone on the same page of how nonlinear getting into quantum computing can be for a lot of us in this day and age. So first, I do want to talk about the fact that, yes, I did get my bachelor's in physics. Actually, is it okay if I stop my video just in case I do have my son come up here? Let me just stop my video if that's okay. Is that okay with everyone? Okay. Just so we can focus, just in case anyone pops up around me. So essentially, yes, I got my bachelor's in physics in 2016 from Dillard University, a small private HBCU in New Orleans, Louisiana. And I participated in research. I did many conferences, won a few presentations, and I was very fortunate enough to be published 3 times for my undergraduate work. So I had a lot of confidence in my ability to do research at that time that I went straight to the PhD. And I ended up getting accepted to a large PWI through a bridge to the doctorate program. But once I got there, I kind of realized quickly that I don't know if I should mention, but like the lack of diversity in the physics program. And this might not be very noticeable to some people, but for me, it was very nerve-wracking. I had very negative experiences, not due to the school, but just the program, I think. I had experiences with like know-it-all teachers who were very annoyed to meet with me or answer any of my elementary questions. I couldn't really get anyone to accept me into their lab. Well, not really. I really just couldn't get anyone to answer my emails about joining a lab there. And so I got really frustrated and the imposter syndrome kind of took over. And so from there, I had an advisor who meant well, but he just kept reminding me how he couldn't identify with my HBCU background. And he didn't know how to support me mentally. And eventually he couldn't even support me financially past my first year. So a lot transpired in this first year of my grad school. And I ended up actually leaving the program with a 1.8 GPA. And no hope on continuing my grad school journey. I don't have it here on my slide of this institution because I don't like to throw anyone under the bus. I just stick to the good parts. But I mention this story because it just shows that, again, even with non-linearity, there are adversities that one might go through, even just trying to get to grad school. So I like to mention that story, that if you go through something similar, you can make it through, because I'm here now. So after this year, I took a little call center job, and soon after felt like so out of place. I felt like I deserved better. And so I knew my potential kind of exceeded that point in my life. But luckily about 8 months into this little regular job, my undergrad advisor, Dr. Abdullah Darwish from Dillard University, he reached out to me and he was trying to see where I was at in life. I explained to him my situation, and then not even a day goes by before he introduces me to this new young professor who just started his lab by the name of Dr. Thomas Searles to let me know that, he's going to take me into the Howard Physics Department, the PhD program. And I remember the phone call like it was yesterday, because I was sitting at my little desk and I literally bursted into tears, because I was like, finally, yes, the second chance. I was like, oh, I gotta really show out at this point, because this is my chance, my shot. Now, as I'm going through the admission process, life kind of hit me. And I found that I was pregnant with my daughter, which I have shown here. It's my daughter, she's 4 years old now. And I was so scared of being judged that I didn't tell anyone. I literally just showed up at Howard's front door when I moved to DC, and I was 8 months pregnant, terrified, because people thought I was fat, but instead I was doing like a month. And so I literally did not let that hinder me in my progression to getting the PhD. So I showed up to lab first day, clearly 8 months pregnant. My lab techs were like, oh no, you're not going anywhere near this lab. I was like, that's fine. I just want to show that I'm dedicated. Moving forward, I did the first 3 years of my PhD in physics at Howard University. And then from there, it was just a lot of late nights, a lot of crying with a newborn. We were both crying at that point in my life, trying to do, classical mechanics problems or quantum mechanics problems. And it was just, I remember it like it was yesterday, because I really thought like I had my second chance, but I didn't know if I was good enough to get through that second chance. But I just kept persevering. I brought my daughter to class with me in her stroller. I brought her playpen to my lab. She was outside the lab door, obviously. I was working with chemicals back then. So, but she was there napping, and she was considered the lab baby. And that just goes to show that I had the best support system while at Howard, through my advisor, through my colleagues, my engineering techs. But towards the end of 2019, my advisor actually told our lab group that we were switching our projects of what we were doing at that time to quantum computing. And I had no clue what this meant, guys. I was like, what is this? What is quantum computing? I have no idea what a qubit is. But what did stick out to me was the funding that was going into quantum computing research at that time. So it was like a little light bulb, like, okay, maybe, sometimes going to something new could be scary, but it might be worth it. So at that time, I signed up for the IBM Quantum Experience. I played around with Qiskit, and then I just started to look up opportunities, to apply the little that I did know into some type of experience or internship. So this was actually where I got accepted into U.S. Naval Research Lab the summer of 2020. Mind you, this was the height of the pandemic, so I didn't unfortunately get to go to the lab, but I think it was a blessing in disguise, because it allowed me to really dive deep into the literature that was out at that time of 2020 of like, where is quantum computing at? Where are we at in the hardware? What are people doing? And I just really was fortunate to get a sense of the industry as a whole. While the project I was working on was synthesizing qubits from transition metals. So the guy I worked with at the Naval Research Lab, he was a chemist who was very interested in qubit architectures. And I thought it was a great opportunity, because it allowed me to start from ground zero of what we see quantum computing, but what is that? And then how does it even work? So we start with the qubit, the quantum bit, the, single unit of information that is in a quantum computer. And so from there, I just was able to kind of like navigate through that system of like understanding all the literature and all the research. And then I was able to kind of formulate a proposal at this time, which fortunate enough was good enough to get this QuaisNet fellowship that Sanjay mentioned in my bio. It was a small fellowship for 3 years to allow me to travel to conferences, but it was a great opportunity because it kind of gave me the confidence that I needed to be able to really get invested into quantum computing and maybe my, my future career. So then from there, I did end up getting the GEM fellowship as well. And that with the GEM fellowship, it's a 2-part fellowship where partial comes from your school and then partial is an employer who interviews you to see whether or not, you can work on one of their projects during the duration of the internship. So luckily, I was fortunate enough to work with ComEd, or the Commonwealth Edison Company, in their research and development department. And they were really invested on figuring out how first of all, grid modernization, but what does that mean? They were really interested in how could they leverage quantum computing algorithms to solve some of their infrastructure issues. So they have a blackout. How quickly can we determine which component of this infrastructure is the reason due to this blackout? And this is the Chicago area or the Northern Illinois area. So, they have some really crazy weather out there. So it was very reputable an opportunity that I got to really dive into the computational side. So initially, I was really coming from undergrad, I was an experimental physicist, but then whenever I got ComEd, it was such a shift. It was a vast shift going into the computational space. I was terrified. I'm not going to lie. I barely know how to work my own computer, let alone code anything. But this opportunity really allowed me the chance to just learn how to code as I go, learn about quantum algorithms, how they work, what problems do they solve, and what is the point? Why do we care, right? And so that was a great opportunity. But by the way, I should mention, yes, during one of these summers, I think it was summer 2021, I was working the Naval Research Lab and ComEd at the same time. And that was me being greedy. This is because if you know how much graduate students get paid, you would understand. I was really just trying to make it at this time. And then I also found out I was pregnant with my son here shown. So I was pregnant, I was doing 2 different projects, luckily both involved in quantum computing. One was experimental, one was computational, but we were still in the pandemic. So I was fortunate to do it all from my computer, and I did some great work. I can't lie. I was stretched thin, but I really made it through, and I felt like nothing could stop me at that point. So from there, most recently, as mentioned before, I did do an internship with IBM last summer on their partner ecosystem team. And I was managing a client that was interested in using IBM's quantum computers. And although this was my most exciting opportunity on this slide, it was not easy at all. I really had to learn what it would take to be successful in an industry role at one of the top producer of quantum computing right now in this day and age. So it was very intimidating. My team was intimidating, but it was amazing. I had wonderful managers. I had, I cried a couple of times, but I really learned a lot. And just to become well-rounded in the space. So I have a little bit of experience from government, from industry, from just like the business side. I just wanted to make sure I was well-rounded because I didn't know what opportunities quantum computing can really give, except for going through these internships. So if you have any questions about that, I'm more than happy to tell you everything. But coming to present day now, I did transfer to the University of Illinois, Chicago 2 years ago, where my advisor, Dr. Thomas Searles, has been guiding me through my research. So during this talk today, I will be discussing my dissertation work, which consists of 2 projects, with the first being on the hardware studies of the quantum permutation algorithm using noisy or intermediate scale quantum processors. Well, noisy, I should say near term, because people at IBM don't like the term noisy. They're very political. So this should say near term. Now, just to give you a little bit of context of what I'll be talking about in this particular presentation is just some background on quantum computing to make sure everyone's on the same page, the quantum permutation algorithm in general, my slight literature review, not too much, and the motivation, the methods that I decided to use to implement this particular algorithm on IBM hardware, and some nice results that I got from the work that I've done in the last year, and then a little bit of discussion and conclusion. Now, let's talk about this quantum computer, because I've been mentioning this buzzword enough, and I don't know who all is on here, but I'm going to assume that some people don't know anything, which is my favorite kind of people, because I love to teach this. So a regular computer, as we all use, with our laptops and our desktops, they're classically speaking, they consist of billions of transistors, right? They're called bits. which are represented as zeros and ones. I don't have this on the slide because I was just going to speed through this kind of introduction. But quantum computers, on the other hand, are based on quantum bits, also known as qubits. And unlike ordinary transistors, which can either be 0 and 1, as I mentioned, qubits can be 0, 1, and both 0 and 1 in a superposition, or a superposition of 0 and 1 at the same time. And shown by this geometrical representation of the state of a qubit is this first figure. This is called the block sphere. And you see that, you have your state 1. This is ket 1, or a state 1. You have state 0. And then this is the wave function, or the position of the qubit when we measure it. And this is considered a superposition of both states. And so from here, the ability for individual qubits to occupy these superposition states where they are simultaneously in multiple states underlies the great potential of quantum computers. For new enthusiasts, you may ask, like, how does a quantum computer even work, right? So a quantum computer makes use of these quantum states of subatomic particles. And physicists are comfortable with like the use of quantum mechanics to describe atomic and subatomic particles and where the particle in question is. And this is mathematically described by Schrödinger's wave mechanics or Heisenberg's matrix mechanics. But however, the state of this point-like particle is described by this wave function. It propagates through space and time according to the wave equation. But essentially, in the end, whenever you measure it, you're going to be given an actual location. So when you want to find out the probability of observing a particle at a particular spot, you need to concern yourself with the wave mechanics. But then, like I said, once we measure it, the wave function is going to collapse to a point in, I guess, on this sphere, for instance. Now, going forward, here is kind of like just an example of what a processor or quantum processor looks like. I just took this off of IBM's website. This is a 433 qubit Osprey processor. It's very nice. This is one of the most recently released qubit or quantum computing processors. And from here, the way this works is that this is actually what they have to use, this dilution refrigerator, to be able to get this thing working. Usually with superconducting qubits, well, there's different kinds that you can use. For example, there's actually different, I like to mention it that with qubit architectures, there's superconducting qubits, there's photonic qubits and transmons that are able to store information. But let's just talk about the spin qubit, for example, which is just a single electron. Like I said, that subatomic particle that we like to take advantage of to do these type of computations. Now, the quantum mechanical nature of an electron has either spin up or spin down. So like, for instance, here, spin up or spin down, or vice versa, whichever. Some people like to talk about the block sphere differently, but just in keeping it plain and simple, spin up or spin down, or superposition of both states, right? So this can be geometrically represented by this block sphere. And then the basis of this technology just takes advantage of the superposition and entanglement of multiple qubits, like on this chip, as I mentioned, to process information. So like I said, on the right, the chip is actually down here. If you look at this whole very confusing structure, the chip is actually at the bottom, and all these wires and tubing is actually the refrigerator part of keeping, for instance, a superconducting qubit, for instance. You have to get it really, really cold for it to work. And that's just based off of physics. If you would like to go into it, we could, but in lieu of time, I'll just keep going. So now that we understand kind of like what a qubit is and what a quantum computer is, we need to do some calculations with it, right? So quantum computers manipulate qubits using these quantum gates, like the example showed in this figure. The gates are applied to qubits, and then the states of the qubit change depending on which gate is applied. Now, in that block sphere representation, the gate provides instructions for rotating the qubit around that sphere. So by arranging gates in a circuit, engineers can create something akin to like a flow chart that enables computers to kind of carry out many kinds of logical operations, such as mathematical calculations, and then perform the kind of tasks that regular computers can do. Now, there are some single qubit gates like shown here, which can flip, for instance, the X gate here, or the NOT gate that we would know classically. Now, this is just a gate that can flip a qubit from the 0 state to the 1 state as well as allowing a superposition state to be created, which is actually given by this Hadamard gate. This Hadamard gate, when you apply circuit, which I'll talk about a little bit in my next slide, this is what creates the superposition of if you're using more than one qubit. And so essentially, quantum gates are the building blocks of a quantum circuit to do these mathematical calculations using linear algebra. Now, a quantum algorithm, right? So now that we know the qubit, we know the gates that we have to apply to the qubit to get it moving. Now the quantum algorithm, this is what we coders need to understand to be able to really get something valuable out of quantum computing or quantum computation. And so quantum algorithm is just the step-by-step procedure to perform a calculation or a sequence of instructions to solve a problem. Now, each of these steps can be performed on a quantum computer, obviously. So for example, here I'm showing the quantum teleportation algorithm taken from the Qiskit textbook, which is using 3 qubits. So this is Q0 or Q0, Q1, and Q2. So these are the 3 qubits, and then 2 classical bits. So these C qubits are the classical bits that one would use to read out the measurement. Now, in this particular algorithm, there are 4 main components of the circuit. So the first one is that you have to start with some initialization and resets that can be performed by a combination of single qubit gates as shown here. And then this from here, we're able to perform the computation or to see the sorry, I got like confused right quick. In real time, we can tell what the classical computation would be by this initialization. And this is shown in Qiskit, which I wish I had a little slide to show kind of like, you know, if you were just apply just these few gates, you'll be able to see in real time based off a simulation what the state of the qubit would be. But just going forward, and then we have this, we apply some other gates, some quantum gates, as I mentioned before. This is a C0 gate and a Hadamard gate. So some entanglement and switching is going on with this qubit. And then lastly, some measurement gates, which is being taken on one of two of the qubits here to be able to read out our measurement in a classical way. And so that's where a classical computer will interpret the measurements of each of these qubits as classical outcomes of either 0 or 1, as shown kind of from that block sphere. And then it stores them in those classical bits. So here, there are just 3 steps that essentially constitute a quantum algorithm. We encode classical data into a quantum state by applying some quantum gates to the quantum state and then measuring 1 or more of the input qubits, or in this case, measuring 2, to determine a classical result. Now, there are various quantum algorithms that solve a variety of different problems, but the one thing quantum algorithms have in common is being able to solve certain, not all, but certain classical problems exponentially faster than current classical computers. So now, one type of problem I want to talk about, again, is the whole point of my presentation, is that, you know, this black box problem. So there are many types of black box problems, and the quantum permutation algorithm is just an example of one of them that can be solved with quantum computing faster than its classical counterpart. Now, the black box problem essentially is just one that can be solved, but the process to solving it is unknown. And the term black box has become kind of just general description for an invisible action or process about which we don't know exactly what is in the black box, for instance, or how it computes, but it does, and it does provide the outputs. So the quantum permutation algorithm, right? This solves a black box problem 2 times faster than the best possible classical algorithm. And I took this from literature with a single measurement to find out if the parity of a given cyclic permutation is positive or negative. I don't know if anyone can see my cursor. Can you all see my, okay, just making sure, because I'm like making sure I can like point to things as well. Now, here we have to talk about this, just what is this, what are we looking at here, right? So this is just a kind of a simplified circuit representation of this quantum permutation algorithm where you have a state of a qubit, just very generalized. And then where you initialize the qubit, you have your state 1, you're getting the state prepared. And then applying a unitary transform, or this quantum Fourier transform, is when we transfer the qubit into another state. So this psi2, or a different position on the Bloch sphere, for instance. And then this right here this is my representation of the black box. It's labeled P because this is what P is, but essentially it's the permutations that are in the black box that we don't know which permutations there are, but we know that we're going to get output. And then once you apply an inverse quantum Fourier transform, that's what this diagram means. We just take the inverse of this operation, and then we have a measurement on the first qubit. So that's why I only included one qubit. And then what will come out is, well, what will come out of the black box is either a positive permutation or a negative permutation, which will result in, if it's a positive permutation that comes out of the black box, then we'll know it because of the state 1. And then if there's a negative permutation, we'll know it because there will be a state 0 result. And the takeaway here is that the quantum Fourier transform is actually the gate that provides the speed up over the classical permutation algorithm. But recently, researchers have shown that there's a modified, or we can modify it by implementing, or replacing, or I guess really taking out in general, the quantum Fourier transform, and still being able to get a result within one measurement. So just to kind of give a little short review of those people, in recent years, the quantum permutation algorithm has been verified experimentally using various methods, including the, nuclear magnetic resonance systems, superconducting systems, and even optical systems, right? But I didn't include those slides on your of these published works just because I want to be mindful of the time. So to only review the main squeeze here, I provided the first demonstration of this modified quantum permutation algorithm shown by Jetic. And so he implemented this QPA, which from what had previously been done, it was able to determine the parity of the permutation in the single measurement using an IBM quantum computer. And since this work was published in 2017, I have to mention the quantum computer that they used for this study has been retired. And the way I look at it is that there's been some major advances since 2017 in quantum computing capabilities. So there are no reports from what I've read that for demonstration of this modified quantum permutation algorithm on current NISQ era quantum computers. And here I just wanted to show IBM's kind of most recent developmental roadmap, just kind of give you an idea where we're at in the industry and this ambitious timeline for progressing just quantum computing over the next, few years. Now, I could not find the old roadmap that mentions some of the first hardware that IBM put online, which again, based off of what, the research has been done before in that previous slide. But this kind of just goes to show that to date, they have met all these commitments with these green checks and are continuing to reach these milestones in scaling up quantum computing. So what we have available, if you have an IBM quantum account, you'll see, if you may or may not have access to, but 27 qubit processors, 65 qubit processors. These two, I think 127 is available for folks. I don't know about this 433. This is the most recent processor online. I don't think it is for like everyday use, but I might be wrong. But I just know I haven't seen it on mine. But this is just really exciting times because when you think of a classical computer, there's billions of transistors. But when we think of quantum computing, do we necessarily need to match that? Do we need billions of qubits to be able to process information? I'm not going to make any, assumptions here, but the whole point is to figure out how can we efficiently scale up the number of qubits that we can use on a chip. To be able to do even more computations than what we can currently do. Now, here is where I show a little bit more about the modified QPA and what I did in implementing it on IBM hardware. So this just shows here essentially broken down of me omitting the quantum Fourier transform and its inverse. So as mentioned before, when you have a quantum algorithm, right, you have these initializations, in this case, a automata on however many qubits. I just put QJ. So my whole purpose is to do as many qubits as possible, but for generalization purposes, then you have your black box, and then there's a measurement taking on the first qubit, which, like I mentioned, if you have a positive permutation, you'll have a state 1, and if you have a negative permutation, you have a state 0. And this is just a plot kind of showing, like, if we were to use the number of like if we were to use, say, the 433 qubit processor, the Osprey, theoretically, we would have millions of permutations that we would have to verify. So essentially, the motivation here is just to implement this modified quantum permutation algorithm on current quantum computers with as many qubits as possible. And the goal is to see if we can achieve higher qubit data from the multiple 5 and 7 qubit systems that we have available. And then we want to understand, if the different hardware metrics maybe influence these results of these larger circuits. So here I just kind of go a little bit into what I did. So initially, the quantum computers in question, right? Let's talk about that. I decided to do my studies on the 5 and the 7 qubit processors because when I first started this project, I had access to higher level systems, but we want to just understand the basic ones, right? The ones with just the very small number of qubits and smaller quantum volumes. We want to understand, what do these numbers even mean, right? And so this important metric that distinguishes hardware from one another is the quantum volume, which is just a measure of the system's capabilities of running a circuit. And then they measure, there was clops on here. There's some other hardware metrics, but for the purpose of my experimentation, I really just want to focus on the quantum volume. And so what I did was I took what JEDEC did from their 2 qubit results, or the 2 qubit permutations that they showed in their paper, and I redemonstrated, I guess, within the Qiskit experience with the IBM X experience online, just to kind of see, verify, okay, through simulations, we either get a state 0 or a state 1, 100% probability of being in either state. And then from there is when I actually coded everything manually into Python or, into a Jupyter notebook. And then from this equation, it just goes to show, as we increase the number of qubits, and based on that plot as well, the number of permutation one has to verify, it grows exponentially. So for the purpose of this talk, I did 2, 3, and 4 qubit QPA circuits using the widely used circuit runner. There's other programs that you can use to submit programs to the quantum computer, but I kept everything very plain. I want to leave it as is, no error mitigation, nothing. I just want to see if it worked. And then for the total number of permutations that I had amongst the 2, 3, and 4 qubit cases, I ran them 5 times each across all these 5 systems and the simulator, just to kind of benchmark the systems against one another. And so going through, so here's just an example of the 2 qubit case. So these are the permutations. This is what's in the black box. So essentially, we have this circuit, but I want to make note of, this is what's inside of the black box as far as, just permutations or variations of knots and C knots. So very simple circuits that one can run and that the hardware can understand. Because one thing I didn't mention is that when you're thinking of the different hardwares, okay, so quantum volume separates them, but what else separates them? So one important, kind of hidden, because it's not unless you do literature review on it, is that each computer has a set of native gates, or gates that they can read that, processes our circuits. So in terms of these gates, these knots and these C knots, the hardware can easily read or transpile these very basic unitary and multi-qubit gates to be able to read a successful, output. So then based off of that, my results for the 2 qubit case here, just kind of, this looks probably crazy, but just to kind of talk about it, one of these. So for Lima, for instance, I decided to do each system benchmarked across, from each other for the state 0 results and the state 1 results. So from here, you can see from the 2 qubit case, because the permutations are very simple, we were expecting, a near perfect result. Not exactly a perfect result like through simulation, but a near perfect result. There's going to be some slight error. And from here, the way we read this, so for instance, for the state 0, this blue bar, for instance, this is the simulation. This is the simulated results for each of these permutations, 0, -, 3-. And for this bottom row, the orange is the simulated results for the state 1, or the positive permutations for 0+ to 3+. And so when we are looking at this, we can see, based on these other colors, they're near perfect. There's really no error. The error would pop up down here because, again, when you're looking at the measurement of either 0 or 1, you'll have a slight error that will show up okay, for instance, 0 minus. We expect the state to be 0 because if for a negative permutation, we expect the state 0. But there will be some very small error in there just because that's just the nature of NISQ hardware where, you know, maybe noise or just external factors might disrupt the measurement just a little bit. So nothing is going to be ever perfect. But here it looks pretty nice. Now, as we go up into the 3-qubit case, there's 8 positive permutations and 8 negative permutations. But for the purpose of the talk, I just kind of narrowed it down to the first 4, like in the 2-qubit case. So for 2 qubits, there is, this is it. There's 4 positive, 4 negative permutations. So 8 total permutations for the 2-qubit case that I had to run. Now for the 3-qubit case, there's 16 total circuits that I ran. But again, I kind of shortened it just to kind of make my results look a little bit more clear. And as you can notice here, now we have not only knots and C-knots, but we also have this funky 3-qubit gate called the Toffoli gate. And this is a very interesting gate because, you know, this is not a native gate to none of the hardware. So if you can imagine what would come next is that we're going to start to see a little slight more error due to this, you know, funky gate. And that's can be shown here. So here is the results for state 0 and state 1. And as you can see, these little bitty bars at the bottom, that's where we're starting to see kind of an error for like 0 minus, for instance. What is 0 minus? Boom, this little complicated thing. There's a lot of gates going on, and then you have to throw a Toffoli in there. So there's going to be a slight error. And I'll talk a little bit about why that's the case in my later slides. But yeah, as we kind of just grow, like for instance here, the 0 minus on Bellum, it's not computing as well, or maybe the 0 plus on Bellum is not computing as well. So we are starting to see a little bit more error. Now, the 4-qubit permutations. Now, in this case, this took me the longest, I feel like, because I had 32 total circuits to run. So I had the 8, and then I had the 16, and then I have the 32. And you can imagine I'm on IBM Quantum all day. Sometimes these experiments are taking me 8 to 10 hours a day, depending on how long the queue times are, because I'm not the only one using it, right? So it's very tedious work. I just have to put that out there. But in this case, now these particular circuits or these permutations, I generated myself. I coded them, I tested them in the IBM Quantum experience to see what kind of state that I would get. And that's how I was able to determine, like, okay, these are my positive permutations and these are my negative permutations, because these produce a state 1 and these produce a state 0. And so when I coded this, now again, this little funky thing right here, I don't know if you want to call this a Toffoli. I call it a 4-qubit Toffoli, just because that Toffoli just means like a CC knot gate. So this is like a CCC knot gate compared to like your regular C knot gates or your regular Toffoli gates. And so based on that is where I go. Now we have some error. We have a lot of error. We're still weighted in the right direction in terms of the state 0 we expect, you know, for these negative permutations, but there is some probability of the qubit also being a little bit in the state 1. That's kind of what these errors represent, is the other state. And so that's just kind of shows, like, as we scale up in qubits, it's getting a little bit more complicated based off of my results. And just to kind of go into the discussion of it a little bit. So what are these Toffoli gates, right? So essentially this thing will break down into this thing. So whenever we're sending these permutations to the back end or the quantum processor, what it has to do, it transpiles our circuit into their native gate set or their native language. And therefore this Toffoli gate breaks down into, you know, a series of 1 and 2 qubit gates that are easily readable. Now, even for this 4-qubit Toffoli, for instance, it breaks down even more. So you can imagine something that looks like this is actually not this. When it transpiles, I wish I had a picture of it, it'll transpile to include many more gates into the computation, which is kind of computationally costing to the hardware. And so I would talk a little bit more about this, but just to kind of go into the conclusion of it, of where I'm at in this project, is just, you know, I wanted to study this black box algorithm on real hardware with as many qubits as possible. And these are my methods, you know, as far as running all these mini circuits with 8192 shots, which is something that you can, you know, change in the IBM Quantum experience. And then I averaged them across 5 samples. Now the results show for my 2-qubit case a 96% success rate. And I probably need to redo these numbers just so I can kind of show each of the hardware, like what is the success rate of each hardware. I just kind of did a large average of what I've gotten so far. So I might need to update these numbers. But essentially, I was able to show a high success rate for 2 qubits and 3 qubits and even 4 qubits, despite, having those errors there. It hasn't been shown before. So one thing that we can do to even mitigate or increase the success rate is like, we can apply error mitigation or any type of extra transpolation to help the back end understand our circuit a little better. And so that's going to be probably for my next steps, is just experimenting with 5 qubit circuits, and then, maybe benchmarking these things on other quantum computing architectures. Because as you may or may not know, IBM is not the only one. We have other different vendors and with different quantum volumes, different hardware. So it's just be exciting to be able to just use this algorithm and just kind of test the waters of everything. And just kind of compare, like, where are we at in the industry? And so just to give my acknowledgments to this particular project, a portion of this work was supported by the Co-Design Center for Quantum Advantage. So thank you all for the opportunity to do this project. The IBM HBCU Quantum Center, the National Quantum Information Science Research Center, and of course, I would like to thank the GEM Fellowship for partial support. Now, to kind of keep going, I hope I'm good on time. I don't even have a watch by me. So I'll just keep going quickly.
Ashley?
Yeah.
Maybe you can take another 5 minutes or so.
Oh, okay, God, I didn't realize I was talking so much. I'm so excited about that project because I've done a lot of work for it, but let's quickly go through this one. So this is my last portion of my work that I'm doing with my dissertation. And this is more so based on the optics, like how can we do quantum computing with a different architecture entirely. And so here I just kind of talk about how can we implement the Deutsch-Jozsa algorithm, which is another black box algorithm, a very early algorithm that is widely known, and how can we use optical computing to realize it. So I'll just go kind of into what we did. So this is just the Deutsch-Jozsa problem, which we don't have to go really into. And then the Deutsch-Jozsa algorithm, which is a little bit similar to the quantum permutation algorithm. So that's why I was interested in using it. And the motivation for this work, we just want to show a different architecture that we can implement quantum algorithms on. And then in this case, simulating the Deutsch-Jozsa algorithm using this quantum algorithm emulator to, operate in terahertz region. Now, this is what optical computing is. It's usually just a setup of a laser, some type of laser source that's being guided and modulated and detected to read out what type of output that we have based on the input light. And so that's a very short, generalized way to say what is optical computing, because I want to get to the good stuff here. So here, this is what we actually are interested in. Now, the Deutsch-Jozsa algorithm can be implemented by this cavity QED or quantum dots or nuclear spins. But in this case, we want to be able to implement it on just this quantum algorithm emulator. And specifically with this photonic device, this is one portion of our algorithm emulator. This is the GRIN lens. And essentially just a GRIN lens is just one that it is an optical instrument that is designed to manipulate, this propagation of light or electromagnetic waves, however you want to say it, to achieve properties that don't occur naturally otherwise. So this is what we did, just some recent research on the fact that, people are using these optical setups to implement quantum algorithms. For instance, here they did Grover's algorithm in the microwave region. And so this just goes into the structure of our quantum algorithm emulator. It consists of 2 subblocks, a Fourier transformer subblock, which is our GRIN lens to read our output, and then this oracle subblock that was shown in the actual algorithm diagram before. And then we did some numerical evaluation of the GRIN lens or this Fourier transform block to just kind of show us this focusing capabilities, that it does operate in the terahertz region, which is very nice. We want to show that this particular material with these varying hole diameters is able to change the refractive index of our lens. And then from there, we just improved the design. So we had this GRIN lens with these varying holes. Our original design, we tested it, it works. Now we want to apply machine learning to it. And we want to apply the machine learning in order to verify our, our initial results, but also make them better. So the way that we did this was in actually collaboration of a Pai-Yan Chen and Yi-Huan Chen from the UIC ECE department. So thank you to them for doing the machine learning portion of our research. I just want to mention. So they implemented this inverse design based on one of the outputs that we expect from this GRIN lens or from the entire structure. And so they were able to train using this neural network model or this inverse design model to be able to kind of better fit our peaks. And so from there, these are optimized results, the red being our optimized results compared to what we initially got for a constant or a balanced function, which I would have gotten into, but we are trying to finish. So these are our output results. We were able to show, that we are able to also, design or simulate a quantum algorithm emulator, like from an optical computer, I guess you could say, that operates in the terahertz region. And the kind of things that we want to do with this is just actually fabricate it and then maybe try to optimize it further for a broader range of incident wavelengths. And then, of course, I want to thank C2QA for this portion of my project as well, the Department of Energy and the Bridge to the Faculty Fellowship for my postdoc. That's it. Hopefully I made time going through that so quickly.
Yeah, thank you so much. Really appreciate it. We are open for questions. And can you turn your camera on, Ashley? I don't know if you.
Yeah, let me turn my camera on.
Yeah.
Okay, let me check the chat now.
Okay. Are there any particular questions for Ashley? And again, thank you so much for sharing your journey and some of the hurdles that you had to navigate through as you get started in this space. So, yeah. I guess I'm curious. So, do we have? Okay, there's a question. Jeremy?
Yes.
I joined, but what parameters are being used to optimize the machine learning algorithms for your last set of experiments?
So according to my collaborators, they were using output performance, such as like the resonant frequencies or the S parameters. I'm not sure exactly what that is, I have to admit, because I didn't do this portion of the research, but that's what they told us, was the S parameters, if that makes sense.
Okay. Anash, you can actually ask the question. Anash. Anash asks, what kind of framework or languages did you use to program and test the algorithms in your work?
So really all I used was, again, the IBM Quantum Experience Online to just play around and actually manually, manipulate the qubits to read the outputs. And then all I did was Python. I opened my notebook and I coded, there's a lot of help out there to be able to get started with using Qiskit in Python. And so it was very nice to be able to just, plug and chug essentially. So I use Python. There's nothing special, not for this round of experimentation. Now there's other things that we can do or we can implement, such as transpilation or optimization, which are, another, a whole nother endeavor. But for this purpose, I only just plain Python and the circuit runner program or Qiskit.
Okay, thank you. Yeah.
I have a question, Ashley, and I want to thank you for sharing with us your technical presentation as well as the story of how your journey has been since entering this field. Considering that you are NC2QA as well as, you have a very unique life story, what would you offer in terms of advice to students, postdocs, faculty who are interested in joining the quantum information science workforce?
That's a great question, actually, because I think about it a lot for myself. I think the biggest advice that I would give anyone that's trying to get into this space is just doing a little bit of research. There are so many different avenues of quantum computing that one can go into that you might not necessarily even I wouldn't say that you don't need to know how to code. Some coding is, might be required, but even just going into the business side, going into the educational side, just a little bit of quantum mechanics, and maybe not even that much, but just a little bit of foundational knowledge, just so you can enter the chat, enter the conversation with experts. And a lot of people are here to help. One thing that I was so fortunate about to have experienced at IBM is that I was having these weekly meetings with software engineers, software developers, high-level coders, and they were very nice. They were so excited to teach anyone that wanted to listen about how to program a quantum computer. And so I think just having just the drive to do it, and honestly, you don't even have to be super bubbly like me. Just putting yourself out there a little bit to ask the right questions to the right people. I think anyone can get into this space, honestly. It's very, very diverse in terms of the work that we're doing. And it's diverse in terms of just the type of opportunities that you can get.
Okay, well, thank you.
So, Ashley, I did have a question. Since your thesis is focused on hardware, what do you think, and I know you have access to superconducting qubits with IBM. What about other hardware platforms? How do you think your results would change on neutral atom or ion trap? Do you expect there to be any difference?
So that's a great question, because I thought about it. So one avenue, so I don't have any access to any other vendor, so let me start there. So I haven't really actually tested my results on any other architecture just yet, but I would think that, honestly, I don't think my results would vary too much, but let me say this, it might. So the reason why I say that, because with the computers that I chose for this work, we have a limited quantum volume, right? That metric that I showed, like what can we actually run on this particular computer? And I wish I mentioned it in my presentation, but the circuit depth of those circuits that I was running, because I have such highly entangled gates, they expand a lot. And so when it transpiles, the circuit depth can easily exceed 32. Like, I think that was the largest circuit depth that I have available, or the largest quantum volume I have available for these experiments. So if I were to test these same, maybe higher qubit permutation algorithm circuits, like the 4-qubit, for instance, where the circuit depths are a little bit larger, I think I would probably get better results on a different architecture that provides me with a higher quantum volume. Because again, the quantum volume is just the measure of how much of this circuit will actually get ran on this computer successfully. And so because, I have some of these larger circuits and they are very big, what I tested on this 32 quantum volume, I'm going to get an error, because they're like, okay, this is a little bit too big for us now. But say IonQ that have, and IBM has computers that have larger quantum volume as well, but just any other architecture. It really just is based on what is the quantum volume of that hardware. And then, yes, I would expect that my results would probably be better on those hardwares, depending, not, thinking about the actual qubit architecture that's being used. Just the quantum volume is what I'm interested in.
Okay, so in general, so as we go through this phase where we are transitioning, I'm old enough to remember when in the 1980s, there were a whole bunch of PC producing companies. And so the question is, who's going to win this race? So you don't think anyone will win. It's just that everyone will be in the game still, yes, no matter what.
Exactly. I think one thing that a lot of people are, so one thing that I feel like from my point of view, from my literature reviews, is that there's not going to be one that's better than the other. I think that they're just all trying to progress towards how can we scale these different architectures up to even do some quality computation, because right now we can only solve a very limited number of problems faster than classical computation, or faster than the best supercomputer, but we're still very limited because of the size of the chips, because of the number of viable qubits are actually being used on that chip. So I think that no one's better than the other. I just think, like you said, everyone's in the game. It just depends on maybe what type of project are you doing that maybe this particular hardware might be able to solve, or compared to others.
Yeah.
Dr. Thomas.
And then Dr. Samuel, just to let you know, I think that's the purpose of C2QA, right? We need a 10 times increase on the software, a 10 times increase on the materials, and a 10 times increase on the actual devices itself. So I would argue that your question is really beneficial for the renewal of C2QA in being that this is something that's important that people need to work on to make these strides to address more than just the algorithms that Ashley was able to look at. But I think it's a great question, but again, it's like the purpose of C2QA in my mind is to increase these things.
Sure. So I'm just curious, Thomas and Ash, you all, I know we are IBM centric because of C2QA and superconducting, but are you actually for your dissertation going to actually get access to IonQ and run?
Yeah, most definitely. So Ashley submitted a proposal to them, and then they're also just in the Chicago ecosystem, there are other platforms that we're taking a look at. But it's in her last study too. So optics and photonics is an option, these other things, because it's really about kind of learning about quantum algorithms and their use on what we can do today. But all of those things are on the plate. And that's, again, one of the good things about C2QA is bringing all these different groups together so Ashley can learn these techniques.
So, and I know you're in Chicago and you probably met Kanav from QBraid. So QBraid does give you access to a whole bunch of different platforms.
Yeah.
So you may want to, that may be something you want to look into.
No, I think that's a very good point from Dr. Samuels. Is QBraid is a friend of our program, but also I think it will be very useful for those that are interested in learning quantum computing and then using these different hardware systems.
So cool.
I'm making a note of that. Great.
Thank you.
So, Dr. Samuel, if I may jump in, I just want to piggyback off of Professor Searle's comment. At Quantum Tech Boston Conference, which took place this week, that was a very common theme about not which one of these will achieve, quantum advantage, but the fact that we need them all to make progress and to really have these useful applications applied. And so I just wanted to co-sign the statement that you made, Professor Searles, and thank you for that question, because I think it's an important question in this field today. And Ashley, thank you for sharing your story. You don't have the traditional linear pathway, and you seem to have overcome so many adversities and challenges while undergoing your studies. And so we are grateful for your commitment, for your perseverance, and for your push. And I'm going to be watching you personally to see how far you go and how far you grow. And I thank Professor Searles for really nurturing you to the extent that he has already, as well as the team over at UIC, Sanjaya and others included. So thank you for your commitment and contribution to C2QA.
Thank you so much.
Yes, I just want to put a plug in to Professor Searles. I just want to introduce you to a couple of your grandchildren. Isaac Lewis, who is here. Isaac, turn your camera on, and Felipe. And these guys are all into quantum because of what the work you've done at the IBM HBCU Quantum Center. So really, Isaac is a physics freshman. He'll be going up to Brandeis to do an internship this summer. And Felipe is a freshman in computer science. And they've spent the whole year learning quantum computing.
That's great. That's good. Start early, because you have the opportunity to start early.
Yeah, thank you for that, Dr. Samuels. And it's great to meet you guys. That's what Quantum Thursdays is about. That's hopefully what the IBM HBCU Quantum Center is about, is to really try to expand the base and get students interested early. So if you guys need anything, feel free to shoot me an email. And best of luck this summer too.
Okay. Thank you. Ashley, thank you all. Thank you all.
Thank you.
Okay. Kim, will you back next week? Yes.
I believe we have one more segment of Quantum Thursdays for this spring series, and then we'll take a break for the summer, and then you can check us out when we return in the fall. Thank you all.
Thank you
all. Thank you. Good. Great job, Ashley. Thank you.
Thank you so much.
Okay. Take care.